You'll see that this new computing paradigm will be based on oscillatory neural networks. And I'll cover some important aspects from materials, devices, architecture, and as I mentioned, all the way to application, which is relevant for Edge AI. So I don't need to motivate this, but I think it's important to mention that the trend that we are currently witnessing in the amount of data is ever increasing. So we are reaching in hundreds of zettabytes, and also if you look into the amount of data consumed per minute, by some of the statistics on internet, is quite they are quite large numbers. And it's important to mention that all this data that are currently processed in the cloud or in data centers, there is a lot of need to be able to process this data at the edge. A lot of these applications now will see that it will become into IoTs or into edge devices, where there is a lot of importance to being able to manipulate, to process, and to be able to adapt and also react to this data at the edge without sending this all the way to the cloud or data centers, given that there is a limited bandwidth, but also there is a lot of power consumption which is actually lost due to this transfer. So the ability to process data or the architecture on these IoT devices to allow processing the data for learning and inference is becoming even more so important. And knowing that, in the coming years, in this decade, we'll see that we'll have trillions of embedded sensors on this type of devices. And it's important to see what would be the underlying paradigms, computing paradigm, and the devices and the architecture and that can allow such IoT devices to be able to process this large amount of data that currently we'll start to witness, which we are witnessing, and even more so in the coming years. And this is even more, becomes a little bit more critical, knowing that how we are actually computing. So what is the current computing paradigm? So you might have seen this on various talks or also from various conferences, that the current computing paradigm or the architecture is based on conventional von Neumann, meaning that we have a separation between the processor and memory. And if we look into the power consumption or the energy, we'll see that a lot of this energy is actually, so let me make this pointer so you can actually see. A lot of the energy is actually not consumed on the computing elements, but rather into the access or the interconnects or in this interface between the processor and memory. And this becomes even more drastic as we go into higher density type of SoCs or systems on chips, and even more into when it comes to real embedded systems, so multi-processors. So it becomes the interconnect, so the data, the bandwidth between the memory and the processor becomes the limiting factor to also how large scale of a system and also how to handle or to be able to learn with this new data that we are seeing, large amount of data that we are seeing. So, and the computing paradigm that I'll be focused about is an alternative to, so going beyond von Neumann, where we have the separation between memory and processor, now is going to a paradigm where you are computing in memory. And this is of interest because this is also very much to what our brain is actually doing, and at a very low power. And the idea is, can we actually emulate some of this brain-inspired or, looking into this biological neural networks to be able to implement them into actual computing architectures. And the main, you'll see and throughout this presentation, the main concept that I will be focusing on is on oscillatory devices. So why this is important? From biological neural networks, we know that neurons have this rhythmic behavior. They spike and fire. And we also know that they are found, and you can see them from EEG, this type of brain waves type of signals, and they are found in neurocortex, hippocampus, olfactory bulb, and they are, from neuroscience, we know that they are key. This type of waves or this type of oscillatory behavior is also key to the memory formation. So the question that I've been posing also with my community and colleagues is, can we actually compute with this type of information? So rather than to spike and fire, where we look into the spike rate and the voltage over time, here we are interested to actually encode the information on this oscillatory signals. So for example, here in this box, you'll see that from a conventional computing paradigm, you can distinguish a 1 from a 0 depending on the voltage over time. So if it's a 1, if it's at a VDD level, and if it's 0, if it's at a ground level. Now, what if you have two signals, such as the blue and the red here, and rather than looking into their voltage difference, so over time, you look into their phase difference. So if they are completely out of phase, like 180-degree phase, that means one is at 0 and the other one is at 1. So you can encode information on the phase difference between such signals. So this is an opportunity to go beyond the conventional computing where you look into voltage over time, but rather now a new way of encoding information. To kind of give you an intuitive feeling, so this is also how we compute from, for example, to perform associative memory type of tasks. So if you start, for example, with a fuzzy image, and the way that these oscillators are coupled with one another, which also creates the memory, performs the associative memory, and it allows you to be able to retrieve what was encoded on this the coupling element of the system. You might have also seen this physics experiment where you have metronomes that start at a random time, and after some time you'll see they're all synchronized. It's the same principle. So oscillators, that the way you couple them, so depending on this coupling elements between them, it allows you to perform interesting functions related to, like, for example, what, as I mentioned, associative memory, but maybe can also do classification, which is more interesting for machine learning type of tasks. So how to do so? With respect to this project, which I'm currently coordinating, NEURON, and this is a European level collaborative project. And the idea here is to build a novel computing architecture, so based on oscillators, where we have the synaptic coupling based on 2D, so transition metal decalcanides, some molybdenum disulfide type memristors. And for oscillatory devices, we have phase change materials, so vanadium dioxide based oscillators. And I'll talk a little bit about each of them and also the architecture and how this is performed. But in conceptually, so without losing generality, what this, in spiking neural network, it's interesting that you are looking into the spike rate because the information is also encoded into the spike rate. So you have to integrate that signal to be able to understand if that's a 1 or a 0. In oscillatory neural networks, we have a different paradigm. As I mentioned, we encode information on the phase difference between the signals. And that is allowed to be a low power because you can really lower the voltage amplitude and also allow multiple phases, so very fine resolution for information encoding. Now I'll talk a little bit more now about what these materials are and these devices. So a dive into materials and devices. So from the oscillator device, as I mentioned, we look into PCM, so phase change material. And the one that we have investigated is vanadium dioxide. So we looked into development of planar devices and also crossbar devices. And this is done in collaboration with IBM Research in Zurich, in Switzerland. And the main interesting property of VO2 is it is a phase change which is triggered by Joule heating. So you'll see that the device undergoes, so the channel undergoes this monoclinic, so M1 to insulator to a metallic phase. And this occurs at about 340 Kelvin or 68 Celsius. So it's interesting to see this hysteresis. So this is the heating where it goes from insulating to metallic, and this is the cooling curve. So this is RT curves. And this is interesting for us because this hysteresis also provides this oscillatory behavior that we will see in the IV curves and also how we use it later as a device for the architecture. So this is the main signature of this phase change material VO2 based device. As I mentioned, we looked into planar. So here, for example, we have a VO2 grown on silicon dioxide, which introduces these granular films, and we have also scaled it to see how these devices would perform. so from micro to nanoscale, but we also have seen that we can achieve very good results with crossbar type of configuration because it allows also a better control of the device performance, and it's also more repeatable and more reliable. So this is the type of devices, so crossbar type of devices that we have been focused more lately. And why this is of interest, because here you'll see when it's a granular film, the RT, it's an interesting, so you can see we have this hysteresis, but it's not very sharp with compared to a nanoparticle, so more isolated nanoparticles. So with larger grains, we can obtain this very sharp transition. And this is interesting because this sharp transition eventually will translate into higher frequencies and also less power to transition. So it's an interesting type of behavior, which for scalability reasons also later, it's much more interesting than a planar type of device. We have performed some DFT, so density function theory type of quantum mechanical simulations to understand the interface between VO2 and the metal contacts. We have looked into platinum and gold, and what we have seen that VO2 creates much closer contact with platinum. And also there is a chemical reactivity, so we have witnessed this as well. And this also changes the thermal interface between the two materials. We've also published recently on this, and also to understand how this device, because we'll see that the crossbar, it's an interesting lot where the current flows. There is also on the surrounding it, but we also wanted to see how much this VO2 and metal interface also impacts overall the device performance. And especially that these are all Joule heating based switching devices. What we have also on the MOS2 side, so on this memoristic devices, what we have been questioning, and also the whole community has been questioning, is what is the underlying mechanism or the memoristic mechanism of MOS2 devices. So is it due to the vacancies? Is it due to impurities? Is it due to so what are the underlying, so the filament creation, what is the underlying mechanism on MOS2? So the main, we did a lot of exhaustive studies to be able to understand, and I think we have some clue, but this is still also to be also repeated by the community to see that really the vacancies and also the impurities are playing a key role in this. Our studies looked into the defect concentration. So we started with sulfur vacancies because these are the mostly widely also what from experimental results is being reported. And we have looked into low concentration all the way to very high concentration, but still we see that the band gap is narrowing, but it still remains a semiconducting type of material. However, into the hypothesis that maybe some of this migration of gold atoms fill the sulfur vacancies, we see indeed that it turns metallic. So maybe this also explains this change in high resistive state or low resistive state is maybe due to this migration of gold atoms into the sulfur vacancies. So this is an interesting insight that we obtained from DFT simulations. And we further went to study what about the number of layers. So can we actually get a memoristic behavior with a single layer MOS2 or with multiple layers? And this was interesting because we also looked into MOS2 with gold. And what we also, so for example, here MOS2, so 4-layer MOS2, and here also 4-layer MOS2 with molybdenum. And what we saw, interestingly, that it's very limited metallization. So, and however, when we have with molybdenum, what we understand is that the very first layer actually becomes metallic, but the rest of the layers remain semiconducting. So maybe a monolayer MOS2 by itself, it's not sufficient to explain this memoristic behavior. So for that reason, we believe that at least 2 or more layers are needed to be able to get such. So this is an interesting study that from DFT, in order to be able to understand what is this underlying mechanism of memoristic behavior on 2D MOS2 material. And so now going a little bit more into the devices, so from the materials, so from the single device, how we actually can build circuits and later on architectures. So again, we studied here from simulations of DFT, TCAD, in order to be able to have this device level behavior and also this to understand the transport and also to have all the parameters that you will get from experimental data, but now also to be able to explore them via simulation and always to go to circuits, so compact models. So what we did for TCAD, we use, the semi-classical transport. So this is TCAD, which is very much drift diffusion and using the, self-consistent equations in order to be able to understand and simulate the electronics transport on semiconducting devices. And this is our approach, and we used from Silvaco, the TCAD tool from them, in order to be able to replicate the VO2 device that we have experimented and we have fabricated. And the interesting is that how this resistive or how this hysteresis is built on VO2 is that it builds gradually over time. And also we model that as a resistive mesh that changes from an insulating to a conductor, so from low resistive to high resistive over time. Because there is at some point in time in the percolation theory and also progress, you'll see that these states coexist till it is fully converted, from a homogeneous, non-homogeneous, and all the way to fully being a transition from one state, so from either insulating to metallic and vice versa. So this is the type of how we actually model this PCM, this phase change material. And what we did is also emulate or closely replicate the fabricated devices, the crossbar fabricated devices that we have developed. So this is the experimental data, the RT. We build the PCM model, so using the TCAD approach. And from there, we can also obtain the IV curve and the key points, which is the insulating metallic transition voltage and also the metallic to insulating transition voltage. So this is the IV curve that also serves us later on to build compact models. So from the compact models, to have a very simple oscillator would require the VO2 device and also an external resistor and capacitor in order to be able to get this oscillatory behavior. And this is what is of interest for us for computing, because we compute based on these oscillations. So now we have a platform that allows us to link the experimental data to a compact model, which is validated and calibrated via TCAD, and now be able to build a compact model for being able to do circuit level simulation. So this is our flow, and we have published quite a lot of papers on this topic. So now how we go to circuit level. So as I mentioned, we have a circuit, so SPICE level compact models based on TCAD that we can now obtain this IV curve and be able to tune this. So rather than using RNC, we can also use an NMOS device in order to be able to tune it. So we are really biasing the device on this NDR region, so negative differential resistant region, to be able to obtain the oscillatory. And we can do this and obtain this also via SPICE or via MATLAB. So we have a very now seamless flow to be able to explore this now at architecture level, what would be the added value. We have also looked into the coupling. So what about the coupling? How would we emulate this? So we have looked both into resistive and capacitive coupling. So for example, with a very low resistive values, the oscillators will tune in phase. And with the very high, for example, resistive values, so weakly coupled, they will actually be out of phase. So you will get oscillatory signals as shown here. So completely out of phase, that means that one is white and the other one is black. So they are out of phase, as in here where they are both in phase. We have looked also to emulate this on PCB just to see, what would be, can we actually perform computation using such concept? And we have also built some, oscillators on a 2x2 and a 3x3 oscillatory neural network to be able to see if we can compute. And we can actually see that we can get a little bit more accuracy also by adding a synaptic a capacitor. So a capacitor, again, this is for discrete here, but it allowed us to explore what would be, can we actually be more precise or be able to have a better control of this in and out of phase using both resistive and capacitive coupling between the oscillators. So this is, again, a representation of how this analog ONN would look like. So as I mentioned earlier, you would start with a fuzzy image, and each of these pixels is an oscillator. And a white pixel as here, it would mean that it has the same phase as the reference oscillator. If it's black, that means it's out of phase from a reference oscillator. And the coupling, it is determined such, so I'll talk a little bit about the learning rules soon, is determined such to allow to memorize. You can memorize numbers like just, for example, 1 through 10 and 1 through 9, or to images such as more into classical machine learning. But this is at first the way we try to investigate the analog ONN is to be able to perform inference. So if for example, it is trained via the Hebbian learning rule, which is an unsupervised learning rule, it allows to retrieve that image. So this is an associative memory task that ONN can perform, which is similar to, for example, more classical recurrent neural network, such as whole-field neural networks. So here you have a little illustration. Let me pointer. So here you have, for example, an input image where you can see the oscillatory behavior, and eventually after a while, after a few cycles, you retrieve the output, what was memorized. So this is so you can see in the beginning, they're out of phase, so they are still rearranging, and then in the end, you will obtain what was memorized. We can also perform some image detection. So depending on how you arrange the network, so this is a fully coupled 10 oscillators, and it is trained in such a way to be able to detect edges. And then from these edges, you can also perform, for example, some image recognition. And these are more classic or the state-of-the-art Sobel and Canny algorithm for edge detection. And this is what we perform with ONN. So still there is some room for improvement in terms of getting, because we obtain more edges than Canny, so the state-of-the-art. So there is still some pruning to do, and we are continuing to evolve or how to reduce the connectivity between the oscillators, so to make it sparse, and also using other learning rules, so beyond Hebbian, in order to be able to have a very good performance with respect to the state of the art. We've also done some estimation, and this is also a TNLS paper that we have submitted, and it was preprint since last year, where we compare how ONN computing paradigm, if it were to build an ASIC, which we are currently taped out and we are waiting for it to come back, how would you perform with respect to other neuromorphic computing paradigms? So here, for example, we have two type of classes. So in blue are the neuromorphic chips, and in red, there are more the digital neural accelerators. And in yellow, it is the ONN with a various scaling. So the current we are here in this paradigm, so it's a competitive paradigm with respect to the energy, even though the switching frequency are depending on the VO2 devices. So we are still in kilohertz to megahertz regime. So it's not a very fast switching type of device, but with scaling and also with external capacitance scaling, we believe that this can become even more so with respect to other neural accelerators and chips and neuromorphic chips. Now, it is important to say that this comparison is done purely on the abstraction of how we compute. So at the neuron level, and scaling it to a certain at the chip level. But it's important to say that we are not including yet here the peripheral or the IOs. So we believe that this trend might be one level a little bit higher. This is still to be validated based on the ASIC measurements that we'll soon report. But we believe that still ONN computing paradigm, it's a very attractive, but also an alternative for very energy efficient at edge level, especially at the edge where you are limited to battery and also power and resources. In terms of benchmarking, as I mentioned, because this is so interesting in terms of computing, we wanted to explore the novel devices, the analog ONN, so ASIC, but also now, what if we actually emulate it in an FPGA? Can we perform some meaningful functions, as I mentioned, associative memory, classification, image recognition? Can we actually use this ONN computing principle, so computing in phases, but now emulate it on an FPGA? And we did so by emulating the oscillators as phase-controlled digital oscillators and SYNAPSES as 5-bit registers, and we implemented them on a ZIBO ZZ development board. And these are some of the stats for 5-to-3 type of networks, 10-to-6 type of networks. And these are some of the applications we have tried. We have tried image recognition from a streaming camera, obstacle avoidance on a small robot with 3 sensors, and also we evolved it to 8 sensors. And then we also did edge detection for image recognition. And these are just some, again, more details on how this work has been developed. So again, there is an image, a fuzzy image from a camera, and then we process that image with ONN on FPGA, and then it's outputted on the screen, what was the pattern that was recognized. So the recognized pattern from the fuzzy image. And here, for example, it's a little demo where we are bringing here in the very bottom, it's the a phone, so a mobile phone with a very fuzzy image, as you can see, and on the screen is the recognized. You see, for example, here is the fuzzy one, and here is what it recognized from that fuzzy image. So it's an interesting for edge type of applications, for example, and we have also seen this on obstacle avoidance via the sensors. And we are processing this sensory data as images from the ONN. So for example, a black bar would mean that there is an obstacle. A white would mean that there is a free angle, there is no obstacles, and the ONN allows to obtain which angle to choose, and it controls the motors of the robot. And here is a little bit of, again, another little demo to show how this robot with 8 sensors avoids obstacles while it's roaming in a space. And we also, so this is just a very high level. We have taken, so as I mentioned, we talked about analog ONN with various devices. So this is something that is currently ongoing to be able to have a demonstrator with VO2 and MOS2. But we also have this digital ONN concept that we have emulated in FPGA that has allowed us to do some applications which are relevant for edge AI, such as on robots, and also with a partner, we have looked into obstacle avoidance on an actual industrial robot, which is E4. So I think with that, I would like to wrap up. I hope I have given you some insights, what it means to compute with oscillators from materials devices all the way to architecture and application for edge AI. A little shout out of my group. So I am currently affiliated on 2 different various different institutions. So in Montpellier at LIRM from CNRS, but also here in Eindhoven University of Technology, where I'm currently also setting up my team. And I would like to also make probably a shout out for potential positions in my team if you are interested and also interested to know more about this computing paradigm or collaborating. Feel free to reach out. And also thank you so much for your attention. And I hope there are some questions I'll be happy to answer.
Thank you, Professor Sanial, for this informative talks. And now I request to all the audience, if you have any query, please unmute yourself and then enter direct to the Professor Sanial. Yes, hello.
Yeah, am I audible? Yeah, sure.
Yes, Ahmed. Yes, please. Please go ahead.
Thank you, Professor, for a very interesting presentation. So my question is regarding the analog ONN part that you demonstrated. So these devices like VO2 and the MOS2 synapses.
Yes.
Can you devices compared
I
Sorry,
think
to like
you
Ahmed,
got
please repeat.
interrupted.
Please repeat. Actually, your voice is interrupted. So please, can you repeat your question?
I was talking about the switching like energy of these VO2 kind of devices that we are targeting in the analog ONN kind of
Yeah.
applications.
So you are asking what is the energy or the power consumption of these devices? So I cannot give you a number on top of my head. I think we
Yeah,
have done
I mean, just
depending on
idea.
the scaling. Yeah, so what's interesting for these devices is, well, first of all, they are very low power. I mean, because they are, you know, the switching is based on joule heating, but you can emulate it via biasing. So that means the voltage you apply on these devices allows, so as I mentioned, there is these two voltages, the metallic, so threshold, the metallic to insulator and insulator to metallic. So you can see that the oscillation occurs between these thresholds. And so the peak-to-peak voltage doesn't have to be very high. It can be actually, you know, very sub-threshold. So it's very interesting for computing because you can really lower the power enough to be able to switch, of course, but for computing purposes, you don't need you don't need like what we would do with CMOS counterparts. So it's a very interesting device for that matter. So that's why the energy efficiency comes in, because device itself doesn't require a lot. Of course, with scaling, you can even lower further that, but with scaling also we see other issues is to, you know, how so with scaling, what we are seeing is that after a while there is no switching because
Right.
there is the crossbar area, it's much more limited, so it doesn't have enough, it doesn't build up enough heat to switch, right? Because you want to pump some voltage to switch the but there is some limit also to scaling. But it's a very interesting device with respect to being low power and also to get a very nice hysteresis, so the sharpness of the hysteresis. Also, the main, I think, work that we are trying to develop now is to be able to see if we can get uniform frequencies across an array, right? Because if the frequencies do not match, now
Right.
that creates a little problem, right? It creates a little problem at the array level and also at architecture level. So how can you compute with non-uniform frequencies? Because the underlying principle is I need to have uniform frequencies so I can match the phases. But if that's not the case anymore, so we have looked into other techniques. So there is a harmonic injection. That means you pump some harmonic into these oscillators in order to be able to allow them to lock. So I don't know if you are familiar with this, but it's very well known in the community that this subharmonic injection allows oscillators to lock. So they can start at random or different frequencies, and after a while they settle down at a common frequency. So there are some tricks to play. But indeed, of these devices, the future as we see forward is not only scaling, but also how to apply harmonic injection in a reliable way, because you need to have an array, right? So scalability challenge is always something very common for these kind of novel devices.
Yeah. Thank you. Thank you.
Yeah, is there any query from the audience?
Yeah, I have a query. Thank you.
Yes,
Thank you,
please.
ma'am, for the wonderful presentation. I have a query regarding the mechanism of the memory strip device based on MS2, which you have
Yeah,
told that the possibility might be there that gold atom will be
yeah,
occupying the
sulfur.
vacant sulfur vacancy.
Yeah,
Yeah, but my question is that the size of atomically the size of sulfur, which is a period 2 element, and gold, which is a period 6 element,
yeah.
doesn't it make create defects in the MOS2 layer? Because the size of if gold occupy the sulfur vacancy.
Indeed. So we made the assumption that we had a very high, percentage of sulfur vacancies, up to 25%, which is And, I cited there, and you can also look into I can also point to the paper we did on this. But the main gist is, indeed, they're not one-to-one, right? So there will be some sulfur vacancies, but some of these will see that there is gold migration on some of them, so not fully, right? And what we are seeing that even a portion or some part of these defects that are filled, or that we see gold migration, we are seeing that there is this band gap you see on the very first layer that becomes metallic. That was very interesting for us. We did not know what to expect, because only sulfur, it became, even with vacancies, is still semiconducting. So to answer your question, we are not saying that it is a one-to-one, I guess, is that what you're after? It's not a one-to-one correspondence. So sulfur with atom, they are completely two different sizes, different bonds. But we are seeing that if some of these are filled because of the interface with gold, we are seeing a little bit, we can see that on the first layer, the metallization. But yes, indeed, they will create defects, they will create non-homogeneous, they will create a lot of other issues, but maybe the mechanism itself is not just a single thing. It's maybe a lot of these things happening at the same time. So maybe because of the applied voltage, there is a lot of sulfur, or maybe because of the growth, if it's CVD or PVD. You see, so it's not just one mechanism. Maybe it is a plethora of these combined together that leads to explain what is causing the memoristive effect. And this is what we are after. We are trying to find the first dominant culprit, that maybe this also is a chain effect on others. I don't know if I explained it correctly, but this is also what we are trying to understand as well. What causes it? Is it multiple cause and effect? I don't know if there is any experts on the audience on this, but at least to us in the community are very much after, what is a 2D MOS2 based memoristor underlying really the physical mechanism.
And second question is, are you using single monolayer MOS2 or multi-layer MOS2?
Multi-layer.
Okay.
Or
Then one reason might be that molybdenum has number of oxidation state varying from +2 to +6. So might be 5 to 6 molybdenum getting bonded with AU.
it could be. So indeed, you see, there are a lot of scenarios, right? And I think that's what the interest on this is, to be able to see. We know for sure that a single layer will not be able to show or to match what we are seeing experimentally. So for that reason, maybe, there are multiple things that are happening. But in any case, we are considering right now a 4-layer type of device. But even a 2-layer, it's sufficient to study it. But we started, as I showed on my sketch, a 4-layer device, and be able to see also if one layer has defects, or some non-uniformities, how that impact the overall device behavior. So this is the type of studies we are currently undertaking. And if you reach out, I can also show you, I can point out to you to some of our recent work on this.
Thank you.
Yeah, is there any question from the audience? Professor Sanyal, one question is from the chat box from Sachidanand. Basically, he is asking about there is a parallel RC in the IMT or MIT design. So, what is the role of this in the modeling of device? The RC element role of the modeling of the device.
Okay.
He is asking.
So the device itself, in order to be able to have sustainable, so you need to have oscillations, all right? So we are using the hysteresis of the device, so going low resistive, high resistive state. But how would you be able to have continuous oscillation? So that's why we have the external, so it just is a basic oscillator design, right? From circuits textbook. So that's why we need the external resistor and capacitor. Now, the coupling between them emulates the resistive value of the memoristor, right? So from a modeling point of view, the easiest way to represent the memoristor, it's a variable resistor, right? So that's why, strongly coupled or weakly coupled, this is how we represent it. But the coupling itself, in order to be able to have a 50-50% of in and out of phase, what we are seeing is that R and C together, so resistive and capacitive coupling, it's a more reliable way to couple such oscillators. And this is what we have shown also on the PCB work. And I'll be happy to share that with you if you know whoever asked that question. We have TNLS, if that's of interest. Look up our TNLS work where we really show how this resistive only and resistive and capacitive coupling matters into the dynamics of an oscillatory neural network. How you can get the phase dynamics, the desired phase dynamics, in order to do a function, for example, you know, pattern recognition or image recognition. So that's why we found out that resistive only is good, but not good enough, so not reliable enough to get the phase dynamics that you want. And the challenge though, so if I can follow up to this question is, okay, so if I scale the network, now my interconnects, so the coupling becomes, you know, they grow quadratically. So they become the most bottleneck. So how this can be somehow, you know, sparsified. And this is where the algorithms, so the machine learning algorithms, you know, sparsity of a network. So you don't need to have a fully. So this is where it comes to place in order to be able to allow still to have resistive and capacitive coupling, but not all fully connected. So there are a lot of, it's a very interesting topic, and this is why I would like to bring more new fresh blood and new brain to it, because it's an intersection of applied physics, device physics, fabrication, but also algorithms. In the end of the day, you want to have something that is practical and you can be useful for something. So that's why it's an intersection of many domains. And I think because of this, it's very rich. I mean, there is a lot of interesting ideas that will come from algorithms and from applications that can allow also, okay, how can I design a good device or a good coupling, right? So maybe it's not just MOS2, but maybe it would be an MOS2 with an NMOS for programmability points of view or for some other reasons. So you see, I'm trying to point out that it's not in isolation, none of these in isolation. All of them are sort of intertwined in order to be able to make an educated guess on how such system can work and scale in time.
Yes, thank you, Professor. As the last question from, I think, is Lakshmi Priya Nanda is asking about the STM analysis. So basically, yeah, I can answer it because the monolayer or bilayer, so you can perform the Raman spectroscopy analysis to mapping that you can easily identify either the MOS is a monolayer or bilayer. Is this relevant to the material science actually, Professor? Identification of the monolayer or bilayer actually.
Yes, so in our DFT, so we are using quantum ADK for modeling this. So yeah, we are using, as I mentioned, up to 4 layers, but 2-layer, bilayer, it's you know, a couple nanometer thickness. It's very, you know, be able to see a lot of this interesting, you know, interface. We have built, our main contribution there is to build this interface model between VO2 and platinum or gold in order to be able to see, you know, what is the presence of defects, their concentration, you know, non-uniformities. So I think that has been very, the starting basis for us to understand, you know, further on the multiple of, I mean, combined effect of these that can explain the switching mechanism on MOS2.
So I think there is no question other from the audience. So let's thank our speakers and thank you so much, Professor Sanial, for giving your important time to our IEEE community and for delivering such a wonderful session on the Edge AI. So
yeah,
thank you so much, Professor.
Thank you.
And
Thank
hopefully
you
we will meet in person the next time at IIT Indore or somewhere else. So
Indeed, there will be events, conferences, and workshops, and
sure.
I encourage if if anyone is interested to know more, to reach out as well. And thank you again for this great opportunity, and happy IEEE Day. It's an important event for a lot of you guys, and also for doing this, for taking the efforts to build such community and also to build such chapter over there. So thank you. Thank you for allowing me to present my work as well.
Thank you, Professor Sanial, and thank you so much. Have a nice day.
Thank you. Take care, everyone.
Thank you. Bye.
Bye.